Welcome students. You are welcome to second part of chapter 1 in unit 3 higher order linear differential equations. In the first part of chapter 1 we learned about higher order linear differential equations and its symbolic form. To continue with the same chapter we move on to learn about the procedure to determine solution of homogeneous linear differential equations of order n with constant coefficients. Let's see the solutions of homogeneous linear differential equations of order n with constant coefficients. If y1, y2, so on yn are n independent solutions of the equation f of dy is equals to 0, which is symbolic form of homogeneous linear differential equation of order n with constant coefficients, then c1 times y1 plus c2 times y2 plus so on plus Cn times yn is also a solution of f of dy is equals to 0, being C1, C2, so on Cn are arbitrary constants. One more thing, here y1, y2, so on yn are n independent solutions means that any one of the solutions y1, y2, so on yn cannot be expressed as a linear combination of the remaining solutions. Now let's see the general solution of homogeneous linear differential equations of order n with constant coefficients. The general solution of the equation f of dy is equals to 0 is nothing but y is equals to c1 times y1 plus c2 times y2 plus so on plus cn times yn. This general solution is also said to be complementary function of homogeneous linear differential equations of order n with constant coefficients. Let us see the procedure to find general solution of homogeneous linear differential equations of order n with constant coefficients. Here, the homogeneous linear differential equations of order n with constant coefficients is given by equation A, and it has a symbolic form f of dy is equals to 0, where f of d is equals to an times d power n plus an minus 1 times d power n minus 1 plus so on plus a1 times d plus a naught. Now we are looking for a function y which satisfies the equation A, which will become the solution of homogeneous linear differential equations of order n with constant coefficients. Let us take y is equals to e power mx be a solution of the equation A. Now we are going to check when will be y is equals to e power mx be the solution of the equation A. For this, we substitute the values of y and its derivatives, which are first order derivative, second order derivative, and so on, nth order derivative in the equation A. We know that first derivative of y with respect to x, that is first derivative of e power mx with respect to x is m into e power mx. Second derivative of y with respect to x, that is second derivative of e power mx with respect to x is m square into e power mx, and so on. Nth derivative of y with respect to x, that is nth derivative of e power mx with respect to x is m power n into e power mx. Now, substituting these values in the equation A, we get an times m power n e power mx plus an minus 1 times m power n minus 1 into e power mx plus so on plus a2 times m square into e power mx plus a1 times m into e power mx plus a0 times e power mx is equals to 0. Now, in this equation, we can take out common e power mx. Then we get the equation an times m power n plus an minus 1 times m power n minus 1 plus so on plus a2 times m square plus a1 times m plus a0 of e power mx is equals to 0. Let us denote this equation with the small letter b. We know that exponential function is a non-zero function for any values in the real number system. So, e power mx is not equals to 0 for all m and x. Thus, we can divide the above equation b by it to get the equation c. an times m power n plus an minus 1 times m power n minus 1 plus so on plus a2 times m square plus a1 times m plus a naught is equals to 0. This equation C in M is called the auxiliary equation, and this auxiliary equation can be written as f of m is equals to 0. Why? Because we know that f of d is equals to an times d power n plus an minus 1 times d power n minus 1 plus so on plus a1 times d plus a naught. Now in f of d, simply replace d with m. We get f of m is equals to an times m power n plus an minus 1 times m power n minus 1 plus so on plus a2 times m square plus a1 times m plus a naught. Thus, auxiliary equation can be written as f of m is equals to 0. Now, in this auxiliary equation, the values m which satisfies the auxiliary equation are nothing but roots of the equation. Hence, e power mx will be a solution of the given differential equation if m is a root of an auxiliary equation. Let's summarize the concept for finding the solution of f of dy is equals to 0. Now, y is equals to e power mx is the solution of the equation f of dy is equals to 0 if it satisfies the equation f of dy is equals to 0, which is the homogeneous linear differential equation of order n with the constant coefficients. For this, while substituting y is equals to e power mx and its derivatives in f of dy is equals to 0, the equation f of dy is equals to 0 becomes algebraic equation in M of degree n. So, y is equals to e power mx will become solution for the equation f of dy is equals to 0 if the value m satisfies the algebraic equation. The values m which satisfies the algebraic equation are nothing but roots of the algebraic equation. This algebraic equation we named as auxiliary equation. Thus, the roots of the auxiliary equation gives the solution form y is equals to e power mx for the equation f of dy is equals to 0. Therefore, y is equals to e power mx is the solution of the equation f of dy is equals to 0, where m is the root of the auxiliary equation. The auxiliary equation f of m is equals to 0 is an algebraic equation in M of degree n. So this equation will have n roots, say m1, m2, so on mn. As we know that if m is the root of the algebraic equation, then y is equals to e power mx will be the solution of the differential equation. So we can have y is equals to e power m1x, y is equals to e power m2x, so on, y is equals to e power m1x are all solutions of the homogeneous linear differential equations of order n with constant coefficients. Now, while solving the auxiliary equation f of m is equals to 0 for the roots, the following three cases occurs. 1. All the roots are distinct and real. Second one, all the roots are real but some are repeating. Third one, the roots may be imaginary roots. Now, we shall discuss all these three possibilities separately to find the general solution of homogeneous linear differential equation of order n with constant coefficients. In the coming videos, let's see how to find general solution of homogeneous linear differential equation of order n with constant coefficients in different cases which arises while solving the auxiliary equation. Let's see what we have learned. We learned the procedure to determine solutions for homogeneous linear differential equations of order n with constant coefficients using auxiliary equation. That is, the roots of the auxiliary equation gives solution form e power mx for homogeneous linear differential equations of order n with constant coefficients. We will meet in the next video lecture, students. Thank you.